Next, let's try deleting an element from the BST. As with insertion, we will study the AVL tree algorithm. Node deletion varies in complexity. For example, deleting leaves is easy, but deleting the root is tricky because the tree needs to remain a BST after deletion. We may also need to balance the tree after a node has been deleted. Let's consider the different deletion cases. Removing a leaf is very similar to inserting a new node. We simply search for the leaf value and disconnect it from the tree. For example, consider the following tree. And here's the same tree after we remove 9. In this case, the tree is still balanced, so no balancing is necessary. If the tree does become unbalanced after the leaf removal, we can balance the tree with 1 or 2 rotations as we did during node insertion. Now let's talk about performance. Unsurprisingly, the cost of deleting a leaf is quite similar to the cost of inserting a leaf. The total cost is equal to the cost of searching the tree plus cost of disconnecting the node plus cost of the balance check and cost of any rotations. This is equal to O log of n plus O of 1 plus O log of n plus O of 1, which simplifies to O log of n. If the node we want to remove has only one child, either left or right, then simply move the child where the node was. For example, let's remove 1 from the previous tree. Here's the result. We replaced node 1 with node 2. The result is still balanced, but again, if the tree lost its balance, we can use the same balancing strategy as before. Now let's consider the performance. Again, we have to find a node in order to delete it, and the cost of disconnecting the node and connecting the child to the grandparent is fixed. Then the cost of deletion is equal to the cost of searching the tree plus cost of replacing the node with a child plus the cost of balance check plus the cost of rotations, which is O log of n plus O of 1 plus O log of n plus O of 1. This simplifies to O log of n. Now let's try to delete a node with 2 children. This is the most interesting case. If the node P we want to remove has 2 children, then we have 2 choices. 1. Find a node with the largest value in the left subtree of P, and replace P with this node. 2. Find the node with the smallest value in the right subtree of P. Replace P with this node. For example, consider this tree. Suppose that we want to remove 5 from this tree. Let's find the largest value in the left subtree. Among the nodes 3, 1, 2, and 4, 4 is the largest. Next, find the smallest value in the right subtree. Among the nodes 8, 6, and 7, 6 is the smallest. Let's replace 5 with 6. First, change the root node value to 6. Of course, we can't have 2 nodes with value 6, so we need to remove the original node. The original node is guaranteed to have either 0 or 1 children because it's the closest node to the root. If this node had 2 children, it cannot be the closest node because one of the 2 children would be between the root and the original node and thus be closer to the root. If the original node has 0 children, it is a leaf, so we can simply remove it. In this case, there is 1 child to the right of 6. We also know how to remove a node with 1 child. We simply move the child into node 6's position. Here is the final result. And here's a video demonstration. Even if the node we're trying to delete is not the root, if the root has 2 children, the same strategy applies. Also, If balancing is needed, the same balancing strategy applies as before as well. Now let's consider the performance of this algorithm. We have to first find the node unless it is the root. And we also have to find the closest node. Then there is the cost of replacing the node, which consists of first, removing the node, 2, removing the closest node, 3, placing the closest node where the node was, and 4, placing the child where the closest node was, if any. All of these steps have a fixed cost. Therefore, the total cost of replacing the node is also fixed. Finally, we need to check and adjust the tree balance. Then the cost of deletion is equal to the cost of searching the tree plus cost of finding the closest node plus cost of node replacement plus the cost of balance check plus the cost of any rotations, which is equal to O log of n plus O log of n plus O of 1 plus O log of n plus O of 1, which simplifies to O log of n. Thus, in all cases, the cost of AVL tree deletion is O log of n, just like AVL tree insertion.